Okay, let's get started. So last time we were talking about harmonic analysis for the group SO3. And we studied a particular example of a function on the two-sphere. So we had some function on the two-sphere, and we lifted it to a function on the group SO3. And then we used the Plancherel formula for SO3 to express the function on the group as a linear combination of matrix elements in the unitary irreducible representations of the group. And then finally, we used the fact that our original function was a function on the two-sphere to derive an invariance condition for the function on the group. And that let us simplify the sum over matrix elements. The main simplification is that instead of getting a general matrix element for an irreducible representation of the group, we got a matrix element where one of the states was this special state 0 that is invariant under SO2. Now, these particular matrix elements between a state that's invariant under SO2, then you act with an SO3 matrix, and then some general state, these are precisely spherical harmonics on the sphere. And so from this point of view, we recovered the decomposition of a function on the sphere into spherical harmonics. What we're going to do now is do an analogous exercise for the Euclidean conformal group. So we're now going to study harmonic analysis for the Euclidean conformal group, SOD plus 1, 1. And the Plancherel measure for this group has support on two types of representations. So first, there are principal series representations. And these are these representations look just like familiar operator representations in CFT, but the dimensions have these funny complex values. So the dimension is d over 2 plus I times s, where s is a real number. And the SOD representation that Peter called rho is any finite dimensional representation of SOD. And for my purposes, I'm mostly just going to talk about traceless symmetric tensor representations. So we'll just say that, we'll focus on spin J representations. So that's one set of types of representations that appears in the Plancherel measure. And then there are so-called discrete series representations. And these will not play a role in our discussion for reasons that I'll explain in a little bit. Okay, so I should say that the principal series representations are unitary irreducible representations of this group, the Euclidean conformal group. And this notion of unitary is not the one we usually care about in quantum mechanics. So the unitary representations for a unitary CFT, as Dalrymple mentioned, the correct way to think about unitarity in that case is they're unitary representations of SOD, 2, the Lorentzian conformal group, or more precisely, the universal cover of SOD, 2. So these principal series representations do not satisfy the types of physical unitarity conditions we usually want. Instead, it's a different type of unitarity condition. So in particular, they're not suitable for appearing in a physical CFT. But their role will be very similar to, in the case, the example from Fourier analysis that we had in the last lecture, where we had a function 1 over cosh x that had some nice expansion in dying exponentials for positive x. And let's imagine that that was supposed to be some Euclidean correlation function. So the dying exponentials are good. Those are characteristic of Euclidean theory. But we expanded it in complex exponentials. So the complex exponentials were just a useful tool for analyzing this function. They weren't actually they didn't have the physical properties that we were interested in, but they were still useful because they satisfy nice orthogonality relations. So these principal series representations will play the same role. The operators that transform in principal series representations are fictitious operators. They're not nice physical local operators in the CFT, but they provide nice bases of functions that we can use to decompose things. Okay. So one important fact about these principal series representations, so I'll call these things E delta J. The E is for Euclidean. One important fact about these principal series representations is that there's an equivalence between the principal series representation and its shadow representation. So here, delta tilde is defined as d minus delta, and I'm going to use that notation over and over. This equivalence happens because there is a conformally invariant map between these two representations. And the conformally invariant map is called the shadow transform.
The script E stands for the representation.
Correct. This is the notation I'll use for the representation. And I'll denote a state in the representation. So here's script E. The basis of states I'll denote by O of x. And if J is non-zero, then O will have some indices. So the rule for how conformal transformations act on these states is that when you act with G on this thing, it transforms in the usual way that primary operators transform. So, okay, so the shadow transform is an integral transform, a conformally invariant integral transform, where if you apply it to O, then it's given by the integral of the unique conformally invariant two-point structure times O of x prime. Now, I'm being a little sloppy here. As Peter discussed, two-point structures, you can have a non-vanishing two-point structure if the SOD representation of one of the operators is the dual reflected representation of the other operator. And I'm going to, in this lecture, I'm really only going to talk about traceless symmetric tensors, where the reflection operation is trivial. So I'm not going to bother writing daggers on my operators. Okay. So the really correct thing to do would be to put a dagger here, but I'm not going to do that. Okay. So the reason this is conformally invariant is that the product of this measure times this thing transforms like a scalar of dimension 0. So this thing transforms like a scalar of dimension delta. This has dimension d minus delta, and this has dimension minus d. So together they have dimension 0, and so you can perform this integral, and the result will respect conformal transformations. Okay, so
What's O tilde?
pardon?
What's O tilde?
Oh, yeah, thank you. Okay, so what this when I write a two-point function or three-point function, in most cases in this lecture, I mean the unique conformally invariant structure for the representations appearing in that function. So what this really means is it's the unique two-point structure for operators with the quantum numbers with the quantum numbers of these things, and O tilde is supposed to have dimension delta tilde. So very precisely, let's say in the case of a scalar, where O is a scalar, this thing is equal to 1 over x minus x prime to the 2 delta tilde. Okay. this furnishes an equivalence between these representations. And in order for this equivalence to be possible, the Casimir eigenvalues of these two representations have to be the same. And that is, in fact, true. So you can look at the quadratic Casimir for these representations, and it's given by this famous formula. And this is indeed invariant under delta goes to d minus delta. So S takes delta to delta tilde, which is d minus delta. And the quadratic Casimir is invariant under that. And the quartic Casimir is invariant as well. And I'm not sure if we'll get there or if it's at all important, but this is called an affine Weyl reflection. I believe affine comes from the fact that you're not just reflecting the weight. So the weight would just be delta, but you have some shift. You're reflecting around a point, around a non-zero point. I think that's where it comes from. Maybe it has other meanings. Okay. Good. Other questions? Okay. So what we're going to do now is study a correlation function, and we're going to analyze it in a similar way to how we analyzed functions on the two-sphere. So let's look at a correlation function in a CFT. And the only important players in this story are going to be the first two operators. We're going to be interested in the behavior of this correlation function as a function of x1 and x2. And so I'll write the other operators as with different notation just to emphasize that they're different. And for example, it won't be at all important for us that these things be primary operators. They can be anything. They could be defect operators. They could be your house, whatever. So we're just interested in the behavior with respect to this thing. And I'm going to put an omega subscript here to indicate that this is a physical operator in an actual CFT. Okay, so the omega is supposed to represent the physical ground state of the theory, and this you can think of as a Euclidean time-ordered correlator of some product of operators in omega. And the reason I'm doing this is because there will be several places where I write 2- and 3-point functions, and they're not supposed to be physical correlators. And this is the first example. I wrote it as a 2-point function, but it really just means this function. Okay? So 2- and 3-point functions without omega subscripts will just represent the standard conformally invariant structures throughout this lecture. And I'm going to try to put the omegas in to distinguish when something's physical and when it's just a function. Okay? Okay. So the first step, in analogy to what we did in the spherical case, is to lift this thing to a function on the conformal group. And so what we're going to do is, instead of thinking of it as a function of x1 and x2, we're going to think of it as a function of a group element. And we're going to have that conformal group element act on a pair of operators at some fixed positions. Bigger. Okay. Yes. Sorry. Okay. So what we're doing here, what this notation means. So first of all, the action of G on a primary operator is given by the usual transformation rule. And in the case of a scalar, we just get omega, which is the Weyl rescaling factor to the delta phi times phi at the new position. So that's what this means. And if you like, you can think about this as you have your correlation function. Here's points 1 and 2, and here are the other points where all the other operators are. And we're surrounding these two guys with a topological surface operator that implements this conformal transformation. And there's something a little funny about this, but some of you might worry that, well, if I act with some random conformal transformation on this thing, I can move them around among the other operators and get into regimes where the OPE doesn't converge. And we're not using the OPE here. Okay? So G is just a way of parameterizing the correlator. And different values of G will indeed move us into different regions where different OPEs are valid. And this is analogous to in the case of 1 over cosh. So 1 over cosh, we had an expansion in dying exponentials for positive x and growing exponentials for negative x, and those are sort of two different OPE regions. But the Fourier transform goes through both of the regions, and that's just how it works. So we're expanding in a basis of functions. We're just using G to parameterize the function that we're expanding in. Okay, so it shouldn't bother you too much that G can be used to move these guys around among all the other operators.
Should they be bothered by G's which will collide one of these points with these?
Good. So that means that this thing this function is going to have singularities as a function of G. That's definitely true, and we should probably worry about the strength of those singularities and what they imply for what we're going to do next. So absolutely, that is something we should pay attention to. Other questions? Okay. Okay, so we have a function on the group. This function on the group, as in the spherical harmonics case, this function of G, so this is we'll define this as f of G. This function on the group satisfies an invariance condition. The invariance condition is that, so invariance f of gh is equal to f of g for h in the stabilizer group of these 2 points, 0 and infinity. And thankfully, Peter saved me several minutes of lecture here by describing the stabilizer group. So the stabilizer group is SO11 cross SOD. The reason that this is invariant under this stabilizer group is, well, so first of all, it's pretty clear that this product of operators is invariant under rotations, because we just have scalar operators, one at the origin and one at infinity. And then the statement that this is invariant under dilatations has to do with that nice picture that Peter drew, where the dilatation, it expands in one way around the origin, but it expands in the opposite way around infinity. So you get a dilatation eigenvalue of delta phi from this guy and minus delta phi from this guy. And would anyone like me to do that computation in more detail? I had it in my notes, but yes? I see some nodding. Okay. So the idea is that, okay, so we have the usual word identity for dilatations, which says that this is x d dx plus delta phi times phi of x. And if we apply this to phi of 0, we just get delta phi times phi of 0. Let's now apply it to phi of infinity. So phi of infinity is defined as the limit as L goes to infinity of L to the 2 delta phi, phi of L. And okay, so we can take this commutator with D and move it to act on phi, and we'll get this differential operator. And then we can pull the differential operator to the outside of everything by commuting it back through this thing. And what we'll get is limit as L goes to infinity of L d dl minus delta phi, L to the 2 delta phi, phi of L. This minus delta phi came from pulling the differential operator back from acting here, back through this thing to the outside. And it's this minus sign that is interesting for us. So the point is that this quantity here converges to a constant as L goes to infinity inside any correlation function. So we should think about this thing as approaching some constant as a function of L. So the derivative is not important. The important thing is this factor. Okay? So, yes?
Why does your definition of the lift of the function on the group actually reproduce the original correlation function?
Great.
So if you try to realize phi's at x1 and x2, then you're going to come dressed with the extra.
Yeah, absolutely, absolutely. So this is right. So you have to be careful about that. So the first point is that by using G, we can pick a G that maps 0 and infinity to any pair of points we want. So this thing contains the same information as the correlation function. But you're absolutely right. When we do that, they're going to come dressed with these factors. Okay? So you're right. So that is not going to be that important for us. But yeah, you can keep it in mind. So in fact, you could write this correlation function as in terms of f of g at some special value of g that takes 0 and infinity to x1 and x2. Yeah. Okay. Good. So these operators have opposite eigenvalues under dilatation. So that means that if we act with a dilatation or a rotation on this product of operators, the result is invariant. And this is analogous to the invariance condition we had for functions on the sphere, where we had a function on SO3 that was invariant under SO2. Okay, so this is very fortuitous, this board technique that I used. Okay, this is going to be great. Okay, so we're in a situation completely analogous to that one. And so here's the analogy. So first, we had, in the previous case, we had a sum from L equals 0 to infinity, 2L plus 1 over volume of SO3. And that was the Plancherel measure. The Plancherel measure in this case is going to be a sum over principal series representations. So we have a sum over spins and an integral over principal series dimensions. And because principal series representations have this equivalence property that E delta J is equivalent to E delta shadow J, it suffices to just integrate over the following range. So from d over 2 to d over 2 plus I infinity. And so we have some integral d delta over 2 pi I, that's a convention, and then some non-trivial function of delta and j. And this is the Plancherel measure. I failed to copy down the expression for mu of delta j into my notes, so unfortunately I don't remember it. I'll try to write it on the board next time. It's some explicit ratios of gamma functions. Yes?
What's G mod H? What's left? Is there parameterization? Like, what's the analog of S2?
Oh, yeah. Good question. What is G mod H in this case? It's some homogeneous space. Let's see. I think it's basically equivalent to. I mean, it's similar to 2 copies of RD because it's basically parameterized by translations and special conformal transformations. But that's probably not the best way to describe it, so I'll have to think about it. The space of all pairs of points. I guess so, yeah. It's the space of pairs of points.
C cross C.
Pardon?
C cross C. Points in RD.
It's the space of these pairs, x1, x2. Kinematic space? Okay. Good. Okay, so good. So instead of this sum over L, we have an integral over principal series representations. The basis elements for the representations of SO3 get replaced with basis elements for these principal series representations. Which again are just a list of objects like this with SOD indices and a position x that transform in the usual way under, as a primary operator does under conformal transformations. The completeness relation for SO3 representations gets replaced with the following completeness relation. For principal series representations. And again, this integral is conformally invariant because this thing transforms with dimension delta. This thing has dimension d minus delta, and so the product of that times the measure is conformally invariant. So this is our basis. This is a completeness relation. Okay, now things get a little bit trickier. So in this previous case, we had this invariance condition on the function f of g. And it allowed us to say that the only matrix elements appearing in the decomposition involved this state 0, the state that's invariant, under SO2. So, okay, so there was an important state previously. In each irreducible representation, there was a state that was invariant under SO2. In this case, in each principal series representation, we should look for a state that I'll denote in this way that is invariant under our well, in this case, this state should be invariant under SO11 cross SOD. Okay, so I haven't told you precisely what this state is. I just told you what its properties should be. Okay, it should be invariant under SO11 cross SOD. For example, you could ask, can we express it in terms of our basis states? And the expression will be interesting. And then finally, we had those coefficients up there, which are the Fourier coefficients. These depend on an irreducible representation, L, and on a choice of basis state in that representation. And so they're going to be replaced with something that I'll call partial waves, which depend on the irreducible representation. So they depend on delta and J. So these are the analogs of L. And they depend on a choice of basis state. So these things here are like M. Okay?
What's the covector that you wrote in the completeness condition? O tilde.
O tilde, yeah. So what is it?
Yeah.
So the important thing for us will be that it's an object whose matrix elements with things transforms like an operator with dimension delta tilde. So I'm about to use that fact. Yeah, it's the complex conjugate of this. And so really, I'm sort of abusing notation here. Usually when we have a state and we write its complex conjugate, we just use the same symbol. But I'm putting the tilde here to emphasize how it will transform in a matrix element, because that'll be important for us. So complex conjugation maps d over 2 plus is to d over 2 minus is. So that's why we're going to have something that's transforming in this way. So I tried to sweep that under the rug, but thank you for pulling it out. Yes.
For the example, we consider the concept of SO3 to SO2.
Yes.
So we have invariance state 0.
Yes.
In this case, I'm going to consider the cosine of SOD plus 1 comma 1 to the SO1 comma 1 times SOD.
Yeah. Yeah. That was actually the question that was asked earlier. So that coset is the configuration space for 2 points. Okay. So so if we want to really write down an analogous formula, we have to ask, what is this matrix element? What is this? So this is just, for now, just a function that depends on these things here. And I'll write down a formula for it later. But previously, these were just playing the role of the coefficients of the spherical harmonics. This will play the role of the coefficients of the conformal harmonics. Okay, so what is this thing? And this is basically sort of equivalent to asking what is this state? We're going to figure out what this thing is by just studying the properties that it has to have. So the first point is it should be it has this invariance under G goes to GH. Because we want this state to be invariant under this stabilizer subgroup. You could also consider G goes to K times G, where K is in the stabilizer subgroup for X. And if you consider that, then you'll find that this thing has to transform basically, you should act with K on this guy. And that transforms like a primary operator in the indicated representation. So you can study different types of group elements and convince yourself that this thing basically satisfies all the Ward identities all the same Ward identities as a fictitious 3-point function Usually we write 3-point functions as a function of 3 coordinates. Here I'm doing this annoying thing where we have one function of a coordinate, and then we're using this group element G to parameterize the other 2 coordinates. The claim is that this thing transforms in the same way as this thing. And we know that Ward identities actually completely fix conformal 3-point functions. So it means that up to a coefficient, this has to be equal to the standard 3-point conformally invariant 3-point structure for operators in these representations. I said it in words, but I'm going to write it on the board because it's important. I learned how to spell fictitious last night. So this is not a physical correlation function. This is just the standard 3-point structure. And because I'm lazy, I'm not actually writing it on the board, but it's just that standard product of distances to powers, to various powers. Okay? So, and it's good that it's not supposed to be a physical correlation function, because these things, what is really meant by these things? So phi started out as a physical operator in a CFT, and here it's really just playing the role as a label for the representation appearing in the 3-point structure. And O is some principal series operator. It's certainly not in the physical Hilbert space of the CFT. So this thing is not like, this doesn't, this whole thing lives in the, if you want to interpret it in terms of a Hilbert space, this is a correlation function in the Hilbert space of principal series representations. It doesn't have anything to do with the physical Hilbert space. But the point is that it's fixed by ward identities, and we can write it down. And I'm writing it like it's a 3-point function because that's extremely convenient notation for writing what it is. Okay? So again, there's no omega here, and that's important. Okay? Okay, so let's finally write the consequence of the Plancherel theorem. So it says that our function f of g is the sum from j equals 0 to infinity, integral over the principal series, d delta over 2 pi I, mu of delta j, integral d dx of this matrix element times p mu1 through mu j delta j of x. So this just comes from taking that thing up there that we already analyzed and making all of these replacements. Okay, so now, right, and this was supposed to be equal to, yeah.
P depends on the x3 to xn.
Absolutely. Yeah, that's a very good point. I was about to say it. So let me just write what f is again. And you're absolutely right. So I'm being a little sloppy here. So this coefficient function here depended on the complete structure of the function on the group that we decomposed into spherical harmonics. And similarly, this p depends on the complete structure of the correlation function we're looking at. In particular, it implicitly depends on all of these other insertions. And in writing this formula, I was dropping that, but in fact, it's probably better not to do that. So let me rewrite it just to make completely explicit what it depends on. So yeah, thanks for that comment. That's important. So okay, so now now I can sort of go back to the thing Chris pointed out. We're using this funny parameterization of the correlation function. We really want it as a function of position. But now we can just look that we have the same thing appearing here and here. So we can now choose a group element that maps 0 to infinity to our two favorite points. 1 second. To our two favorite points. We get some factors of omega here, but we get the same factors of omega here, so those factors just cancel. So we can write this in a more conventional way by getting rid of the group element and just writing that 5x1, 5x2, b3 through bn is equal to this sum over j, integral over delta, u delta j, integral b dx, 5x1, 5x2, o tilde mu1 through mu j of x, p delta j, mu1 through mu j of x, x3 through xn. There was a question.
You mentioned that discrete series should also appear here.
Thank you. Yeah, actually, this is the right time to mention it. So discrete series will not be important for us, and the reason is that there are no non-vanishing matrix elements for two scalars in a discrete series state. So discrete series could potentially appear if you tried to do this exercise where you didn't start with two scalar operators, but you started with non-scalar operators. But since we're doing scalars, they're not going to appear. Yes?
So it wasn't important that you pick the action of G on two operators. Like, in principle, you could have accessed the entire correlation function on
Act on the entire correlation function? Or?
No, you could have parameterized.
Any subset.
Yeah.
So absolutely, yeah. You can do this exercise. You can absolutely do this exercise for any subset of the points in the correlator. That is, an interesting thing to do. The thing that gets complicated is that instead of this state that's invariant under SO11 cross SOD, you now have a state that is invariant under the stabilizer subgroup that Peter talked about. So if you did 3 points, you would have a state that's invariant under SOD minus 1. If you did 4 points, SOD minus 2. And eventually, with enough points, it wouldn't have any invariance condition at all. And when you have fewer invariance conditions on your state, it means that these matrix elements can be more complicated. And actually, the summary of what the matrix elements can be is essentially, well, it's the analysis that Peter did. So the question is, what are the structures that are possible for, so let's say we did 3 points instead of 2 points. You would be left with asking, what can the matrix element be between this and a state that's SOD minus 1 invariant? Turns out they're classified by 4-point tensor structures.
So is there more than one representation of the same correlation function?
Absolutely. I mean, yeah, but we're familiar with that. That's yeah. There are many different ways of doing it, and maybe I'll draw some diagrams in a little bit to give a sense of the possibilities.
Why not choosing just one? Sorry.
Pardon?
Why not acting with G on just one operator? Then you would have obtained something just like the same. So in that case, would it be simpler?
Good. So I think if you did that and you tried to use an operator that was, so first of all, let's suppose that phi were a principal series operator. Okay, this is not a likely situation, but let's suppose that it was. Then if you did that, you would find that the matrix element, that you would find that the partial wave was basically like a delta function, fixing delta to be exactly equal to the dimension of that operator. And so you would find sort of like and this matrix element would also be a delta function. You'd find a trivial statement. If you didn't have a principal series operator, then I think what would happen is that there would not be a normalizable state with the correct invariance condition. It would be like trying to decompose a single exponential in terms of a Fourier series. So, yeah, I think you would just be looking at the fact that there's a single irreducible representation in a very confusing way. There's a question, yes?
Is there any reason why you're not summing over the representation where S is negative?
Where S is negative? S?
Like in the principal series, you have S being zero.
Oh, yeah, I said that. So the reason is that the representations with positive S and the representations with negative S are equivalent representations because of the shadow transform. So if I, well, let me, I'll clarify that in a little bit. But basically, there's just no new information in the partial waves for positive S versus negative S. Okay. Yeah, so one thing I should say is that this exact same logic, so something like this might look sort of familiar to some of you. So precisely this logic can be used to derive the split representation for propagators in ADS. So that has the same sort of flavor. You start with a function of 2 points. In this case, what you do is you act with a group element on one of the points in ADS, and you sort of rewrite that in terms of an integral over the boundary. So there's an integral dx and an integral over the principal series of some things. And again, in that situation, you can compute the matrix element using various invariance conditions, and you find that it's the bulk to boundary propagator. So I'm not going to go over that in detail, but for those of you who are familiar with that, that's the way to derive the split representation.
So A4I, this formula is derived with all the phi's and all the b's in the principal series.
Good. So
You add a continuum to the actual values of the dimensions that appear. Can there be poles across the contour of the integration?
yes. Yeah, absolutely. So this relates to some questions that were already asked. It relates to Slava's question. It relates to the question that you asked. So the most rigorous setting for all of this is where as you said, everything here transforms in principal series representations. In that setting, then you indeed get this nice contour integral. One way to get to more physically interesting settings would be to analytically continue from the principal series representations to physical representations. And when that happens, you can indeed get poles crossing the contour, and you need to keep track of what happens. Just as a comment, this I don't think is like a non-starter for this whole set of techniques. So I think it's just complicated. It's something you need to keep track of, but it doesn't mean that these formulas don't apply in those general cases. It's just that the simplest theorems that people write down are for the simplest cases. So you have to derive your own theorem.
Also, this is not important if the dimensions are equal.
That's right. Yeah, that's absolutely true. So yeah, if the dimensions are equal, yeah, so that's right. So the way that the dimensions of these things come in is in the invariance condition for the state. More generally, so here we had a state that was invariant under SO11. If they had different dimensions, then you would get some, when you act with SO11, you would get some phase that depends on the difference of the dimensions. And, you get some factor that depends on the difference of the dimensions. If they're principal series representations, then that factor is a phase and everything is nicely behaved. But if their dimensions are equal, then there's no phase and there's nothing to worry about. Is this related to a melon amplitude? I don't think there's like a deep relation to the melon amplitude. This is a way of writing the 4-point function. The melon representation is also a way of writing the 4-point function, and so you can relate them. Okay. Yeah, that's a great question. So, in principle, you could try doing something like this in Lorentzian signature, and it hasn't been worked out. The Plancherel formula is more complicated in Lorentzian signature, as was mentioned earlier, and there are some features of Lorentzian signature that would make this kind of a weird thing to do. So I'll just say one thing, which is that. So here we get these integrals like this, these integrals d dx, which go over all of Euclidean space. In Lorentzian signature, the analogous integrals would go over all of the Lorentzian cylinder. That might be fine. It might be mathematically correct, but it's a sort of physically bad thing to do sometimes, or you might be worried about it physically because you would be studying properties of correlators at very, very large Lorentzian time. And the physics at different Lorentzian times can be extremely different. And usually we're interested in physics at, well, it depends on what you're doing. But the physics in different, at very, very large Lorentzian time is controlled by, I don't know, chaos, all sorts of weird stuff. The physics at short Lorentzian times is controlled maybe by the OPE, maybe the Reggie limit. There are all sorts of different limits, and if you're integrating over the entire Lorentzian cylinder, you're kind of mixing all of these up. So it kind of has the wrong flavor from that point of view. But I should say, as far as I know, no one's really tried it in detail, and maybe it would be interesting. Okay. Good. So now I'm going to talk a little bit about conformal integrals. Which we need to actually start doing some computations with this stuff. So the first point is that you can integrate a function that transforms in some principal series representation times a function that transforms in the shadow representation in a conformally invariant way. And again, the reason that you can do this is that this thing has dimension d, this thing has dimension delta, This is dimension d minus delta. This is dimension minus d. The sum of all of those things is 0, and so this integral respects conformal invariance. And if these operators have spin, then you need to contract their spin indices. And I'm often going to suppress the spin indices. So if you see O times O tilde at the same point, then you should imagine that their spin indices are contracted.
Is there such a thing as an integral that respects only scale invariance?
An integral that only respects scale invariance. I'm not sure of a good answer. You're saying that, oh, I just checked scale invariance and we got conformal invariance for free. Yeah, I mean, I think you could probably do that sort of thing if you involved descendants in the integral. Yeah, some product of descendant operators. Okay, so so this is a nice conformally invariant pairing, and using this pairing, we can write down a nice pairing on endpoint structures. So if we have an endpoint correlation structure, I'll say, so not necessarily a physical correlation function, just some function that transforms in the way indicated by these representations, and then we have another one with the shadow representations, then we can pair them. And the subscript E is for Euclidean, so this is a Euclidean pairing. And the rule for the pairing is that you integrate over all positions of just the product of these things. But there's, okay, so good. So we're just using this thing n times. But there's a problem with doing this. Does anyone see the problem? It's translation invariant. Good. Okay, so it's translation invariant, so that's bad. There's actually more than just that. That's right. It has complete conformal invariance, and the conformal group is non-compact. For example, it contains translations. So this is infinite. So what we can do to fix it is divide by infinity, particularly divide by the volume of the conformal group. Because we're physicists, we're not scared. We know exactly what this means. What this really means is that you have to gauge fix the integral, introduce a fideo Popov determinant, and then proceed. But this is an extremely nice way of writing it because it makes manifest the symmetry properties of these integrals, and we'll use that over and over. So let me give an example of what the fideo Popov procedure looks like in this case. All right, so as an example, let's look at a three-point pairing. So we're going to study a pairing of two three-point structures, one with representations 1, 2, and 3, and another with the shadow representations. And so, okay, so what we should do is gauge fix the conformal symmetry. So we can use conformal transformations to place the 3 points, x1, x2, and x3 in some standard configuration. And a nice choice is putting x1 at 0, x2 at some unit vector e, and x3 at infinity. So this is different from the standard configuration that Peter chose, but that won't really matter for us. So after we've used conformal transformations to fix these 3 points at these positions, now the points are fixed. There's no integral to do. So we're basically done. It isn't actually an integral. It's just a product. But we need to do a couple things. So the first thing that we need to do is stick in the fideo Popov determinant. And that will be on the exercises, which are, this is not online yet, but the fideo Popov determinant for this choice of gaze fixing turns out to be 1/2 to the d. And then there's this configuration has some leftover symmetry. So there are some gauge transformations that are unfixed by this choice. And that's precisely the stabilizer group that Peter talked about. So we have these 3 points on a line. And we can do SO d-1 rotations around that line, and that leaves the 3 points fixed. And so we need to divide by the volume of that remaining, of those remaining gauge symmetries. And so, for example, in the case where all 3 operators are scalars, then each of these factors is just 1. Okay, so these pairings might look a little scary, but for 3-point functions, there's no actual integral to do. For 4-point functions, there's just a single integral to do, and we'll talk about that in a little more detail later. Okay, so the chalkboard gods are with us again. We have exactly what we need up there. So we know that the correlation function has this expansion in this expansion I'll call the conformal partial wave expansion. And so we like to write down a formula for these coefficients, these coefficient functions, p delta j. And to do that, we can use this bubble integral. And I'll explain why I'm calling it a bubble integral in a second. So it's a bubble integral because I can think of these, each of these 3-point structures as some trivalent vertex. So this thing is a trivalent vertex where this is x, this is x1, and this is x2. And here I'm integrating it against a shadow 3-point structure. So I'm connecting up 2 of these lines because I'm putting both of these operators at x1 and both of these operators at x2. And this is x prime. So that's why I'm calling it a bubble integral. It turns out that this is equal to our 3-point pairing divided by the Plancherel measure times a bunch of delta functions, delta of everything. Okay, so here delta for O is d over 2 plus is. Delta prime is d over 2 plus is prime. And in writing this formula, I'm going to restrict to s and s prime bigger than 0.
Very simple way to understand why Blanchard measure comes out of this calculation.
Yeah, there is. So there's a sort of goofy way to derive this formula that I think is also correct, which is okay, so what you do is you write that this bubble is equal to some unknown coefficient times delta of s minus s prime. You set s equal to s prime. I didn't expect to talk about this. So here's O and here's O prime tilde. So you set s equal to s prime, and you get something that looks like this. And now, and so what is this? Really, sorry, I skipped a step. So this is equal to this times a Dirac delta function in position space, which you can think of as just the identity transformation, which I'll draw like this. So now we do this, and now we take the trace of both sides. So this thing becomes that. And this thing becomes that. The claim is that, so this is a trace in an infinite dimensional representation. And sorry, it's, okay, things are, sorry, I'm going to say stuff that is going to be really silly. It's a trace in an infinite dimensional representation, then you have to divide by the volume of the group, which is also infinite dimensional. Turns out you should think of this as something being like something like 1 over infinity, and then it gets multiplied by infinity, and the combination of all of this stuff is the Planck-Scherl measure. And this is a 3-point pairing. So there are some graphical rules that you can use that will not lead you astray in these types of computations. This actually is a really nice way to see why this formula holds. Yes?
Why did you set s and s prime both to 0? I mean, if that's really you're going to try to continue to reopen piece that right?
Yeah, okay, so this is, don't pay too much attention to what's in the box. Why did I set s and s prime to 0? So, oh, I set them equal.
No, I just meant positive. So in the above expression.
Oh, yeah, why am I doing this? Yeah. Good. So the reason that you can do this is that representations with s goes to, there's an equivalence between s goes to minus s. So suppose you want to derive this formula now for the case where one of the s's is negative. What do? You shadow transform both sides. And that's an exercise in the problem set. Okay? So this actually covers all cases if you're willing to do shadow transforms. And if you don't restrict this, then there are 2 terms, and it looks much more complicated. It's harder to understand. This is simpler for us. Okay.
So at the end, you want to analytically continue to s equals 0? Can anything go wrong here?
So we want to analytically continue to imaginary s, namely real delta. Let's finish going through the analysis, then we'll talk about the analytic continuation. But yeah, it's a reasonable question. So I don't think you should not try to analytically continue this bubble formula. That's not a good idea. The bubble formula has this delta of s minus s prime in it, and it really doesn't make sense when you go off the principal series. So we're going to only use the bubble formula on the principal series. Then when we're done with the computation, we can ask whether we can analytically continue or not. Okay, so good. So we have this bubble formula, and it means that we can now write down an expression for this partial wave. So what we do is we take that expression up there, and we integrate against a shadow. We integrate over x1 and x2 with a shadow 3-point function for phi of x1 and phi of x2. So I didn't actually get the boards in the right place anyway. So. Okay, so we have our correlation function. And then a shadow 3-point function. And again, this is just the standard conformally invariant 3-point structure, and this is the physical correlation function we're interested in. And a cartoon for this is that here's the endpoint function. The partial wave is given by taking two of the points, 1 and 2, contracting it with a 3-point function, and doing the integrals. So let's apply this to an example. Which is a 4-point function. In the case of a 4-point function, we have now a 4-point function. And we're integrating it against a shadow 3-point function in a conformally invariant way. So we have an overall, the object that we have, maybe I should write what this actually depends on. So this is x, x3 through xn. The object that we have depends on now 3 points. So we have x3, x4, and x, and it's conformally invariant. So it has to be proportional to a conformal 3-point function. So in the case of a 4-point function, we must have that p delta j of x, x3, and x4 is equal to some function of delta and j times the standard conformally invariant 3-point structure. That's just fixed by conformal invariance. Yeah. Oh, good. Thank you. Yeah. Thanks. Thanks a lot. So I'm now going to study. I'm going to study a 4-point function of identical scalars. So I'm going to replace. So now the v's are going to get replaced with 5x3, 5x4. Thanks. Thank you. Okay. Good. So now let's plug that in up there, or rather up there. So we find that the 4-point function is equal to a sum over j, an integral over the principal series, mu of delta j. Okay, and now we're going to plug in our expression for the partial wave. So we'll plug in this expression for the partial wave. So we get I of delta j times an integral d dx phi of x1, phi of x2, O tilde of x, O of x, phi of x3, phi of x4. And I'll call this thing psi delta phi. It depends on delta and j. So everywhere here, delta and j are the dimension and spin of O. And it's a function of x1 through x4. And I'll call this a conformal partial wave. So, so we have this thing that is that depends on delta and j and the 3 points, and it can be expressed as the integral of our 4-point function against the 3-point function. So, because the integral is conformally invariant, the result depends on only 3 points. So it depends on x3, x4, and x, because we've integrated over 1 and 2. And therefore must be proportional to a conformally invariant 3-point function. So I is just the coefficient.
So why don't depend on conformal wave of phi?
I? What does I not depend on it?
Why this term don't depend on conformal wave of phi? It only depends on conformal wave of the O.
Oh, yeah. So it does depend on, it can depend on the conformal weight of phi. I'm imagining the case where phi is like the sigma operator in the 3D Ising model. So the weight is, it's not a parameter that we can dial. Everything depends on it though, yeah. Okay. Good. So I'm trying to remember when I started. Anyone have any idea? Okay, I think I have maybe 5 minutes. No one asked you. Okay. Good. So this is a conformal partial wave, and I think Peter is going to talk a lot about these integrals later in his next lecture. So, and maybe we'll also have something on the problem set about it. So it turns out that this conformal partial wave is a linear combination of conformal blocks with some coefficients that I'll call k. So times conformal blocks. So specifically, it's a linear combination of a conformal block, a standard conformal block, plus a shadow block. This is the standard block with dimension delta and spin j, and this is the block with dimension d minus delta and spin j. If you take this expression and plug it in here, it turns out, and this will probably be on the exercises if I get around to writing it up. It turns out that, so here there's a sort of symmetry between delta and delta shadow. And this symmetry is precisely what's needed to extend the integration range from d over 2, from half of the imaginary axis, so from here to here, to the entire imaginary axis. So here we use symmetry under delta goes to d minus delta. This expression is not precisely symmetric under delta goes to d minus delta because we have these two different coefficients, but the two different coefficients turn out to exactly match the symmetry property of the coefficient function I of delta j. So what you can do is replace this integral over half the imaginary axis with an integral over the whole imaginary axis and drop one of these terms. So this can be alternatively written as a sum over j, integral over the entire principal series of some function c of delta j times a conformal block. And this function C of delta j is mu of delta j, I of delta j, k delta tilde j delta phi. And the relationship, so this gives a way of writing the 4-point function as an integral over conformal blocks. And the relationship between this and the standard way of writing the 4-point function is similar to the example that we talked about earlier with the Fourier transform of 1 over cosh. So the idea is that here we have an integral over the principal series. And we should imagine that this coefficient function C of delta j has poles on the real axis.
What do you know about this coefficient function, general graphs?
Good. So the coefficient function, you can write a formula for it. You can write two different formulas for it, the Euclidean and Lorentzian inversion formulas. And you can use those to study its analytic properties. And in particular, you can use those to argue that it has poles precisely on the real axis if you start with a physical 4-point function. I'm not sure that everything is known about this function, but certainly this property you can check. It has to do with the fact that the poles come from the OPE region. So in the OPE region, you have some good understanding of how the 4-point function behaves, and you can really analyze the inversion integrals for C. Okay, so C has poles on the real axis. You take this integral over the principal series, and you deform it to pick up the residues of those poles. And the poles should have the form that their residues are let's see. I mean, well, so we had a talk by Sasha about that a couple months ago. I think the statement is that if you write the coefficient function in a shadow symmetric way, so you use shadow symmetric conventions, then I think the statement is that it grows, it's polynomially bounded at infinity and delta. And furthermore, the coefficients of each power of delta are, at large delta, are polynomials in J, something like that. I mean, that's just some fact about it. I'm not sure what the most general thing you could say is.
It's hard to argue, because you see, originally this function is given by some integral which converges only in a certain strip before the first pole.
Yeah.
Then you go to the first pole, you have to subtract it.
Oh, you're interested in what happens in the
Yeah, I mean,
in the whole complex plane.
yeah, you have to close the contour.
Yeah, out here.
So what happens there?
Yeah. Okay, that's a fair question. Yeah, I'm not sure what the statement is there. I was talking about just on the principal series. I mean, I would be surprised if something terrible happens there. We know that the conformal block expansion is a true way of writing the 4-point function, and we know that this is a true way of writing the 4-point function. It would be pretty weird if this weren't the way that they were related, but I guess maybe it's possible.
When you pick the poles, you are not picking the poles to the left of that.
Yeah, good. So thanks. So
Could be that those are contributions related to those. No, I mean the physical operators that live on the left-hand side.
oh, yeah. Good. So that's right. There are subtleties that have to do with physical operators whose dimensions are to the left of the principal series. That's absolutely true. And I don't want to talk about those right now, but maybe I can talk about them a little more later.
Could it be that they are related to contribution of those operators?
Potentially, yeah. Yeah, you have to, yeah, good. So, okay, everyone decided to wait till the last minute to ask about all the subtleties I was sweeping under the rug. Maybe I'll try to say something about them next time. But I just want to finish this discussion for the moment. Okay, so you're supposed to imagine that C of delta J has poles of this form with a minus sign. So when you deform the contour, you pick up the residues of those poles, and that gives you, instead of an integral over dimensions, it gives a discrete sum of dimensions, which is the conformal block expansion. And I think I'd better stop here.